This is the Tesoro AI podcast with Darius Gant. AI is changing the world and fast. This episode is coming to you courtesy of Tesoro AI, the #1 recruiting service for software development and AI talent.
All right, Robin, welcome to the show. I appreciate you taking some time to join us.
Thank you, Darius. It's a pleasure to be here.
Absolutely. So before we get into PhysicsX, I thought it was interesting to see you spent some time on the sciences side at some pretty reputable auto manufacturers. So high-end luxury. We've got, correct me if I'm misstating any of these. We've got Mercedes-AMG, Formula One team, as well as Bentley Motors. Would love to, especially kind of your experience there as the chief scientist and in your other role as vehicle technology director. Would love to hear, how if it was the case, AI was being applied.
Well, great. I mean, I went into Formula One. I'm a theoretical physicist, and you build theories, you do simulations, you try and predict what caused the evolution of the universe and to be it like today, and then you wait around for a few decades until experimental evidence emerges that either validates or disproves your theories, right? A bit impatient. So, that's a lot of waiting around and fine-tuning and things like that. So I went to Formula One because every Sunday you find out whether your theories that you're working to are right or not.
Right.
You get your race, you get your finishing position. There's real truth to that. So yeah, went to first to Renault F1, now Alpine F1, then to Mercedes F1 as chief scientist and head of research and development. And what you learn there is you've got this really fast interaction between theoretical development, so numerical physics simulation, lab time simulation, CFD, finite element, and whether it's actually faster or not. You've got that proof point really fast, and that fast iteration cycle is a really great technology incubator. So if you want to try machine learning methods to optimize designs, to optimize vehicle setup, to learn about tire performance, you have real test data from a real car really quick.
Yeah. What were some of the applications of machine learning that you all were using? And, curious why machine learning or AI was the route to go.
Yeah. So at the time then, so much was still built around numerical simulation. And in fact, in F1, it was one of the incubators of numerical simulation. If you think
Right.
about vehicle dynamics simulation, lap time simulation, tire modeling, things like that, performance modeling. So the first thing you recognize is when you want to invent something new, a new system on the car, these tend to be complex. They've got sort of design parameters that you're trying to get your head around. What's the best configuration of this new thing? Let's say you make a device that changes the right height of the car, right? So many valves, actuators, little orifice, and things like that. And as a human, it's really hard to figure out what the best configuration is. I've got 15 different variables to play with. What's the best overall one? So use machine learning to orchestrate that process. How does that work? First, well, a machine learning agent tries one configuration, that through a simulation. It kind of learns if that was better or not, or at least it's the first one. On the second one, it learns if it's better than the first one or not. On the third one, it takes the learning from the second one and it changes the parameter configuration in order to evolve that full parameter set to an optimal state. An optimal state may be the lightest car, or the quickest lap time, or the strongest design, whatever it is that it's optimizing. So machine learning optimizers interact with the virtual representation of the car to drive the configuration to an optimal state. So that was the first application.
Got it. So as you were exploring newer versions of the car, machine learning was allowing you to test in a more cost efficient way, right? Versus, hey, if I've got 15 different variations, you to actually create those in the real world, it's going to cost a lot of money and time. So this was a better way to experiment.
Exactly right. That transformation from numerical simulation to virtual, I'm sorry, from physical testing to numerical simulation or virtual testing does exactly what you said. It saves money because I do a virtual crash test. I'm not destroying an expensive $1 million prototype, right? It's just a virtual
Right.
thing. It takes technology, you got to develop it, then there's time and money spent on that. But overall, this is how companies develop in advanced industries, how they develop their products now. It's faster and it's cheaper. And then the
Mhm.
machine learning on top of that, in the past, the machine learning helped orchestrate and automate that process over and over again to get to a best design. Now, the world has changed. In the last half decade, technology has been developed academically by us and other companies to replace the numerical simulation as well. So that
Okay.
means that rather than, numerical simulation taking a few hours to solve airflow around a car or some structural problem, we can now use deep learning models to do the same thing. In fact, at PhysicsX, we've just released the very first large physics model for flight. So that is now the same, a large language model. You can ask a language model a question, it gives you an answer, right? This large physics model, you can show it a geometry, and it gives you the flight performance of that geometry, lift, drag, stability, things like that.
Yeah. And getting to PhysicsX, curious, what was the impetus for launching the company? Was there a particular pain point that you saw that needed to be solved?
Yeah. So, firm believer in previous responsibility, whether it was in F1, but also then as my role as technology director was really driving virtual development, including machine learning optimization in those industries. But PhysicsX really wanted to scale that beyond just automotive. Our
Mhm.
mission is that we're really relevant across advanced industries. So aerospace, initially also
Mm.
medical work and renewables, clean energy, materials, semiconductors. And so we have grown into this whole advanced industry space now and find that our technology is relevant there and delivers faster path to product, faster value, higher performance, people less time.
Yeah, interesting. So your experience with kind of what I'll say is like a vertical use case of AI in the automotive industry, in the physics space, you look at across the universe of problems that could be solved, and you're like, look, you know, great to do this work internally as part of Formula One, but the technology itself it can be applied more horizontally.
Absolutely true. So you take the wing of a Formula One car, obviously the analogy to a wing of an airplane is there, the blade of a wind turbine is there. But what's really amazing, the same foundational technology in terms of the foundation models that we've built and so forth, they also
Mm-hmm.
translate to something very, very different. They translate to something like the strength of a part. They even translate now to some multi-physics and chemistry interaction models that we have
Mm.
learned that we can predict on. And the more complexity is involved in all of those physics, when we talk physics, multi-physics, like the simple example is when got aerodynamics, flow of the wing and performance that creates, an internal structure of the wing. So, how's the wing built? How much does it deform? And then when the wing
Yeah.
deforms, that changes the aerodynamics. So that simulation takes a long time if you want to do that
Right.
accurately, because it's a lot of interaction between these. And however, with deep learning, we can do that very, very quickly, all at once in a single model, and scale that across more physics and even including chemistry.
Right. And so for the ability for an airline, for example, to do that same level of testing that you were mentioning for Formula One, it's also going to save them costs. It's also going to create efficiency or new product designs or improve safety simply because they can go in there and they can run these simulations, figure out what's working, figure out what's not working. One thing I thought about, with large language models, with these foundational models, you got an explosion of these generative AI tools for video, right? Runway ML is one that comes to mind. There are others out there. Physics becomes an issue for a lot of those. And what do I mean? So if you see two humans walking or any type of activity that's happening by, with an object, right? It doesn't always work out correctly. One video I remember seeing is one person was cutting a tomato and then he just cut through his finger, and then continued cutting, right? And for an AI model, that probably made sense to create. But us humans, we would look at that and say, okay, clearly this is fake, right? So the physics, from what I hear, right? But I'd love to get your opinion. Physics appears to be the issue in the generation of these videos. What's I would love to get your opinion on anything related to that, but I was curious what the major challenge is.
I mean, Darius, you've got your finger right on the pulse right now of the technology. There was a fantastic paper that just came out a few days ago, authors from DeepMind and others. And the title of the paper is, Do Generative Video Models Learn Physical Principles from Watching Videos? And the answer is no. You can't
Okay.
learn physics from watching from watching videos. And this is high quality 3D video data. And the correlation, so the accuracy was between 10 and 20%, So the point is that this macroscopic view of the video, this macro behavioral observation, doesn't give you enough information to learn physics. Yet our models can learn physics. And why can they learn physics? Because our models are trained on simulation data, which has all the detail. It knows about all the flow field. When you look at airflow, well, you don't see the air. A video doesn't capture that. It doesn't see the velocity vectors. It doesn't know what the pressure distribution is, right? It doesn't even necessarily know what the temperature distribution is. It doesn't learn anything about the real physics. It learns macro behavior. So you can learn a bit about mechanical objects, how they interact. The correlation was highest for that. But for like airflow and thermal behavior, the correlation was lowest. So the answer is no, unfortunately, the way it looks right now and for, short to intermediate future, you cannot learn physics from 3D video or observational data like that. It is absolutely true that if you have data quality, data refinement, data quantity at the level of microscopic data, then that you can learn physics. Talent. We talked a lot about physics, right? So our talent is scientists and engineers that can decode a physical problem, let's say, in producing a product and optimizing a design, in optimizing a process on a manufacturing floor or in the operational context, and can find a way to represent that. The first step is to represent that in simulation. So we have simulation experts. The second step is to generate synthetic training data, which our simulation experts do. That data trains models. So data scientists train models, build new foundation models. Machine learning engineers build all the pipelines and the interactivity between the simulation data, the foundation models, the optimizers, and then software developers produce our product, which is a platform in which you can operate all of that. So the talent we have are software engineers, data scientists, machine learning engineers, simulation engineers.
If you're a hiring manager and you appreciate the unique skill sets required to build AI solutions, then I would highly suggest you get your hands on our AI talent salary guide. As you know, one of the greatest challenges in building AI products is acquiring the right team. Over 100 plus pages, we dive deep into our global AI talent acquisition strategies. And with our networks in Latin America, we also provide you with actionable advice on how you can scale up your AI team cost efficiently. Once you explore our AI talent acquisition strategies, you'll never look at hiring the same way again. Links are in the description.
Yeah, and just thinking about this comparison between simulations, right? What you're talking about are simulations in a more narrow scope of the word. When I'm mentioning movies, right? This is a 2 hour. If you create a movie with AI, you've basically created a 2 hour simulation. In a movie, you're showing various different types of terrains, vehicles, human activity in that 2 hour piece. So to use a large language model, and I'm trying to understand kind of what the gap that you mentioned was. So for the large language model that is being used to simulate scenes, it doesn't understand the unique relationship or physics between the objects because it's only been trained on video. What you're saying in this more narrowly defined case, you've got data that tells you how a car can accurately,
Yeah,
a plane can accurately fly through the sky in different types of weather, right? And that data can then be used by AI to produce a more realistic simulation to where us as the human viewer, we can it look real.
good. So the answer is yes. However, when we talk about simulation at the level of simulation for games or simulation for special effects, it's not simulation, it's imagination. Sorry, what's the physics inside? You looked up the bonnet, the hood, and you look underneath. What's the physics inside? Typically tends to be the type of smooth particle hydrodynamics, which is entirely empirical.
Mhm.
Interactions defined as distances between objects, and that's it, right? And that's not really physics. That's so totally empirical. Physics doesn't happen like that. Fluid dynamics doesn't happen like that. Even mechanics only happen in different types of headwinds and weather and things like that, and that will be a realistic representation. But to do that is unbelievably compute expensive. To do a
Mm.
simulation like that will take you hours and hours just for a few seconds of an airplane flying. So to
Mhm.
scale that with numerical simulation to a video context is impossible. That's why these simpler physics models like smooth particle hydro, which run very, very quickly, can be used for that and produce, very convincingly looking results that aren't real physics, but look like the real world at a macroscopic level.
Yeah, it sounds like we'll continue to have, because I think video generation is a super interesting space, but it sounds like we'll still continue to have that issue that we even have today. Movies where if you're a specialist, you see the movie and you're like, maybe so someone in the military may say the actor would never, a military guy would never hold the gun like that, right? Similarly, if you got video generation created by AI, right, it would look very realistic if we're talking about creating simulations or AI generated video in the way that you're explaining. But on the larger scale, it's like, specialists are going to be like, hey, this is not how things actually work.
But there's something really cool. Not that we're doing this anytime soon, but what we do is we replace the super time-consuming, high-accuracy simulation, physics simulation, by
Hmm.
physics models, large physics models that are as accurate as the simulation, but they run in a second. So all of a sudden, you can think about simulating, now really simulating, an hour's worth of flight if you wanted to, right? Because
Hmm.
the compute cost and the compute time has come down by a factor of 10,000 or 100,000 for that. So it could be an application that, hey, let's do video now with real physics in the loop.
Yeah, when you produce these simulations, because at Formula One, you were mentioning simulations, but it was math,
Yeah.
right? Does the simulation also need to include some video component? Does someone actually need to see? So if it's a flight, do they need to see the flight? If it's a crash, do they need to see the crash? Or can they just read the data and
So,
understand whether something is.
fantastic question. You need both, right? So, a really important thing in Formula One, when you do a CFD simulation, right, you test a bunch of different geometries and you get a result. The lift is, or the downforce is higher, right? Negative lift is higher. The drag is lower. That's good, right? So, there's hard data that is
Mhm,
generated by a whole bunch of data processing afterwards in the simulation that tells you that's faster. So, that's just a number, and that's a very valuable number to have. But the engineer that is
mhm.
designing the surfaces, that engineer, he or she wants to look at the flow field. They want to understand how the change in geometry affected the flow so they have an understanding about how can I generally move more in this direction of a better flow field, a higher performant flow field. Why is this geometry better? And for that you need visualization and oftentimes video visualization
Mm.
to understand how the flow is involved in curling and where the vortices are and all of that. And so the CFD simulation as an output called post-processing can represent images like flow fields, maps, pressure maps, and also video. And that's very informative to the human.
Yeah, how do you mentioned crash testing? In a scenario where someone was using PhysicsX to explore how to create a safer car, plane, whatever it may be, you've created the simulation, you got the data, you got the video. Still seems to be a gap between trust. Okay, if I actually do get in the crash, how do I know that? How do I know that Physics X got this right?
Yeah, well, okay. So a couple of things here. So, for example, crash testing. When we work with companies, automobile OEMs or
Mhm.
aircraft producers for which crash testing is really relevant, they are already expert simulation. They're expert at that. So they have simulation models that have been validated against a real crash test, right? And they operate those models and they create the training data for us to train our deep learning
Mhm.
models on. So this is quite important because there's already a ground truth that has been validated back to a
Got
real world experiment. That was an expensive experiment, right? So then when we train on this data, we provide them a faster solution that as
it.
long as that simulation model was validated, our large physics model maintains that validation. And when our large physics model comes up with a strange shape for some crash column, for example, how can we trust that? There's mistrust in AI and large models and things.
Right.
Well, it's really
It's
easy.
hallucinations, right?
Yeah, exactly. Yeah. Well, we take that new geometry that's supposed to be performing better, and we run that back through the numerical simulation because that's already the customer owns that, has spent years, decades even validating that against the real world. So we take that geometry that our AI model came back with and say, hey, let's run it through your normal process, your simulation process. Okay, great. If it's better in the simulation as well, we've got a good candidate. Then they will take that and then we'll create a component test. Just let's
Mhm.
not do a whole car first, let's do the component. Great, works on the component test. Now let's invest and put that into a prototype, into the next car build that we do and crash that in the whole car. So you go
Yeah.
through these stages of maturing the content of your virtual and physical test to where you get to the full system level, the whole car, which you can then write a sign off.
Got it. And I want to dig more. You mentioned large physics model. I want to better understand what you mean by that. If we're thinking about large language model, most folks have used ChatGPT not by now, or Gemini, or one of the several that are out there. Large physics model, how should we conceptualize what that is?
Oh, fantastic. So what does large mean, right? Um, Large means it's literally has many, many layers, has, up to around 1 billion parameters. It's sort of, I think, it's like level of GTP1 or something like that, roughly. So it's
Mhm.
large for as far as deep neural networks go. And well, the physics means it has been trained on physics data.
Mm.
So, like we said, synthetic data, but we've also trained on experimental data, high accuracy experimental data, doing both, right? But it's physics data. And it's a model, meaning that you put on the input something that you want to have an answer to. So, a geometry, you can put in a geometry at the input, you can put in that whole mesh, the whole shape of that geometry, and the model predicts what the performance is of that geometry, the strength of the geometry, the aerodynamic behavior of that geometry.
Interesting. So, okay, so let's parallel this to ChatGPT. In
Mhm,
ChatGPT, large language model, I'm going to go in, I'm going to put in some text, right? Some
mhm.
that, and I want a response. I could include within that text now math problems. I can include a range of different language prompts, and I'm going to get that back. Until some extent, some other use cases, you can get video and images. Large physics model. Am I writing text into a prompt? Am I
Yeah,
uploading an image? Like, what's engagement like?
great question. You can do both. So we've just a couple months ago released something called Airplane, and it's spelled AI.Rplane. And you get to the interface and just go to our website. You can get the link to it directly. Anybody can play with it. And you can put in text, and the text can say, hey, I want you to design an airplane that, fits in my garage, so 2-meter wingspan. or drone or whatever. It's got to carry 100 kilograms of load, and it's got to fly some distance, and I want to get there in this amount of time. What does that look like? And after a few seconds, it throws up a map of all the possible designs that you might be interested in that fulfill this requirement. Those designs are the shapes. And with the shape, you immediately get the performance. So there's the shape of something that looks like a glider. Well, the performance is it's not very fast, but it's very light, probably large wingspan. And then there's something that looks more like a delta wing. Oh, that's going to be fast, probably can carry a bit more load as well and whatever. And so you get that performance very quickly, but you get the real physics performance, the pressure fields, the drag, the lift, and all of that. So you can interact at the level of prompt. So prompt to design is exactly that. And another thing you can do is you can upload a geometry you have. Oh, let's see, I've designed this thing. How well will this fly? You upload that into Airplane, and we predict on it. And you can modify it and make it better. We have an optimizer that improves it, and then you can download the new shape and you can go off and 3D print it.
Yeah, one of the interesting use cases that I noted of AI agents, there was a example of, I believe it was Claude computer use, was used on a YouTube video to observe a construction scene, and the question asked to Claude computer use was, "Hey, find all of the safety risks." And so it watched the video and then spit out, what it thought would be the safety risks. Now, no, we don't know if that was all of them. We don't know. There's a lot we don't know, but it was interesting that an agent could be used to do something similar. Do you have any? And I don't, if that's a secret on the product roadmap, I don't. I don't want you to spill the beans, but I'm curious if you have any thoughts around that, because you're talking about being able to input a prompt, and then I get, some design out. What immediately popped into my head was, okay, now can I have a agent observe the design and then give me other information about, potential risk, or, is there any, do you see any use for agents as you think about kind of what we were discussing?
Absolutely, and a great question. So yeah, we can talk about a few things. I think they're highly relevant in this space, right? But relatively unexplored. And for us, there's sort of a simple interaction level that when you interact with our design agent, our design tool, Airplane, you get feedback. Hey, this isn't a great idea. There's nothing really that fits this space. You want to look over here. So there's a bit of that interaction. But at a much deeper technical level, in our product, in our software product, there's an agent already built in. And what that agent does, it automatically, we can engage it or not, but when the model itself, remember, this is a data trained model, right? Model trained on data. When the model uncertainty gets a bit large, it's going far away from the training data set. It's seeing new geometries it hasn't really been trained on before. The agent recognizes that, and it immediately kicks off one more simulation to retrain the model in that new design space. Now, that's the process when you have a model that hasn't been fully trained yet. Our large physics model for flight has been fully trained. So it generalizes now across all shapes that fly, and you don't have to retrain this anymore. But in most contexts, you don't want to invest that much pre-training effort. So this is a really surgical and easy way to use an agent to be laser focused on only doing as much training as you need. But I think there are so many more applications and opportunities with agent, but I think that is a journey to come.
Yeah, very interesting. I mean, agents are a topic that I think it'll be transformational. Today, I haven't really seen many that really move the needle. For the most part, I've seen agents that are being used that are more focused on research, which I think can be helpful depending on what you do, but still in the early phases of what agents ultimately accomplish. Is that, I know you've built some internally, right, for your team. Is this something that's on the radar for you, or do you have enough on your plate with cutting edge AI that already exists at PhysicsX?
It's absolutely on the radar for us, and it's part of if you think about when you go through an engineering process or workflow, you want to
Hmm.
automate as much of that as possible, right? So if you
Hmm.
can automate a construction site risk assessment, can we automate all the data pipelining that happens when we put workflows together, different libraries together to create a workflow? So super relevant. It's a faster way to get there for our customers using the tool. Nobody really cares about building a workflow. You just want the pipeline to work and you want to get the
Right.
result, the optimized result out.
Right. Right. Yes, the space I continue to kind of keep an eye on. You get these wild statements that I'm saying it's wild, but maybe it's possible. You had the Salesforce CEO mention they weren't hiring any more engineers because now they're using agents to accomplish tasks, and now they have to figure out things for their existing engineers to do. So I always want to keep an eye and see, kind of how much of this is AI hype versus, I should say, future pacing. I shouldn't say hype. Let's just say AI future pacing, and how much is like in action today.
All I can tell you that in our technology, which is very scientific and physics and engineering context based, we're a long way away from that. And we don't seek to displace the engineer. We seek to empower, give them superpowers. For a
Hmm.
lot of
Hmm.
the automation, the engineering judgment, like I said earlier, the engineer understanding really the airflow around the car and modifying the design based on that, the ability to come with experience and engineering judgment to see the multidimensionality of a problem that
Hmm.
an AI workflow doesn't capture, might not capture the manufacturing context or might not capture some aspects of the product user. That's super important. And what you want to decomplexify and debottleneck is all this cumbersome, numerical, time-consuming process to get you
Hmm.
to the answer. So we empower engineers by getting them to the answer and the selection of the optimally balanced design faster.
Yeah. Are there any parts of the product we haven't talked about yet? I kind of jumped around there, but anything we haven't talked about, use cases we haven't talked about that you think are particularly interesting?
Well, we talked around design optimization, but there, in a product life cycle, there's two other functions that were relevant in manufacturing. So
Hmm.
whether that's additive manufacturing, so 3D printing, or in more continuous manufacturing or casting. So these are all use cases where we are working with our customers, they're using our technology in order to improve castings, improve smelting pools, improve 3D printed objects and the 3D printing process. So happy to dive into that. Operations. So, for example, helicopter OEM we're working with, a very complicated viscoelastics or polymer bearing that supports the blades, and they
Hmm.
bend and you can't really measure that. It's quite expensive to measure. It's not part of the normal helicopter. In the operation of flying the helicopter about, what's that bend angle? It's called the flap angle. What is that? And the sensor is super expensive and cumbersome to carry around. Can we use a machine learning driven methods to estimate that? And the answer is yes. And so that feeds back directly, that operational data feeds back directly into the design path. Now I know all those bend angles as a function of time. I can feed that into my helicopter flight model. I can also use that for fatigue data, fatigue analysis, or failure prediction of that bushing, that viscoelastic bushing.
Yeah. Yeah. I remember the case study where car manufacturers, obviously parts come from all over the world, various parts of the world, and specific vendors sell very, specific, unique products. What you're saying, it sounds like from an operations perspective, if there was a vendor who potentially is out of that product or you can't reach that vendor for one reason or another, or even maybe even close the business, substitute products may come into play here where you could understand what other products may fit to make the system work. Am I understanding that correctly in what you were saying about operations, being able to understand what different components could be replaced or could be used within the entire system?
I think this is maybe a little bit more around bill of materials and things like that and substitutability. It's not a use case that we've will engage in, and I'm not exactly sure of how, takes a few deep dives, but I'm not exactly sure of how our tech would really be applicable to that. It's really when
Mhm.
you're talking about like in-field operations, a wind turbine in a field, when the wind's too strong and the temperature is too high, it has to turn itself down. It's called thermal
Mm.
derating, right? So to predict that is super time consuming. Our deep learning model can predict that very quickly. And it can forward predict that. It can play the, if I put a wind turbine on this side, how much thermal derating do I get? And it can crunch through a year's worth of dating and tell you, I'm going to get that many total hours of thermal derating. That's how much power I lost. And then the manufacturer can go back in and can say, ooh, but if I put a larger cooler on that, will I get less thermal derating? And the answer is yes. And if it costs you, you gain that much extra energy, and they know how much the cost of the bigger coolers. So you can do the substitutability that you spoke to at the component level and find out what the impact is then on the performance.
Got it. So the focus is more on performance versus the parts themselves. And then you mentioned 3D printing. What do you
Mhm.
guys? How do you all play in that world?
Oh, we love 3D printing because, I talked earlier, I explained a little bit, you can put a prompt in, right? And it designs
Mm-hmm.
you an airplane, and then you can go and print that 3D airplane. Well, 3D printing, you don't have to think too hard about the manufacturing process. You don't have to think about, can I machine that? What does the bit look like for that, right? You can go from
Mm-hmm.
that shape to the manufacturing to the toolpath very, very quickly. And there are some limits, like for metal printers, you can't print horizontally. You have to kind
Okay.
of print up or print at an angle, right? But we can make that part of the optimization. Don't make a structure that has to go horizontal across that. We do that, right?
Ah.
And you can only print that thin, but no thinner. Okay, there's another constraint we bake into the design optimization model. But so 3D printing has a lot of geometric shape freedom. And when we look for maximum performance, having that freedom allows us to push shapes in that direction and not have to worry too much about whether that is manufacturable or not.
Yeah. So when you're working with these manufacturing companies, who's the primary user of PhysicsX?
And so it's talked a little bit about simulation engineers, right?
Mm-hmm.
So they sit in the process where they get an early design, a very
Mm-hmm.
early design, and then they have to come up with something that now meets the performance requirement or is lighter or stronger, whatever, right? So this is where we empower them to move a lot faster
Mm.
rather than having sitting for days and weeks at a time to wait for the answer. They can have that in a day. So that's one core user. Another one is a design engineer that may not have any simulation experience. And when they have a design, they then have to hand that off to a simulation engineer who might be busy, wait a while, they
Mm-hmm.
get it back, and then goes back. And this human trade-off interaction handoff is common. So we build tools for design engineers that can sketch something, build something in 3D as a model, and immediately know how it performs. The last user is a technician. So a QA assurance technician, somebody who has to make sure that the part conforms to a drawing, right? Now can make sure that the part performs to a performance metric. So when I get a scan of the part, in the past used to say, oh, that scan is dimensionally accurate. It matches the CAD reference, but doesn't do here. Throw it in the junk pile, right? Throw it in the bin. Now, with the scan, they can go immediately and say, oh, this now is actually the air resistance of this part, or this is the thrust that the turbine makes, or whatever it is. This is the strength of the part. And even though it dimensionally doesn't conform quite, if it still has the strength that it needs to have, great.
Mm-hmm.
If it still produces the thrust that it needs to have, keep it. Don't throw it away. So there's a number of users in the companies that we work with across from, advanced method development, simulation engineers, design engineers, even to the operational floor.
Nice. So you built a tool where the team doesn't necessarily, I mean, they don't need a data science team, machine learning team. They can really use their kind of, what's the word for it? Subject matter experts, right? They can use their
Yeah,
subject matter to
Yeah,
interact with the tool versus having to have this entire, data team, machine learning engineering team.
absolutely. And with customers that have that expertise, that have data scientists, machine learning engineers, they can then fully interact. They can interact at a level of building new applications, of
Mm.
designing their own workflows. So where that experience exists, absolutely, then they are empowered to do more. They can import libraries or machine learning models they have used before that they like, and it all interoperates. So something
Yeah,
for everyone.
I'm curious. Your team now, you all are based. Is it a global team, or are you more like, what's the word? Not bi-coastal, but I think you operate out of more than one
Yeah.
country. I think it may be two. But would love to learn more about how you built the team out.
Well, we started on a airbase, a historic airbase in a small office near Oxford, then moved to London 2 years ago, a bit more than 2 years ago. Then moved again in London. We moved in December again. We're about 110 people now. We opened our office in New York half a year ago. We've built this out. We have a managing director in New York. We're duplicating to some degree our expertise that we have in London, like the people
Hmm.
that work closely with our customers, the people that deploy our software, the training and things like that. So we're across Atlantic now is maybe the word to look for. And for a company of our size, I mean, our primary markets are in Europe and in North America. It's well fit to what it is now. Obviously, North America, we work a lot on the West Coast, also on the East Coast. So it's a big stretch, and over time we will stretch across that country more into more locations. Eventually, also move into Asia. But right now, that the focus is North America and the EU and Europe.
Yeah, and then in terms of the tech team, the specialists in AI, the AI engineers, how do you think about building that team out? Are they also cross Atlantic, or does that team specifically sit in London?
So we have sort of three main functions. One is the
Okay.
research function, then there
Hmm.
is the product development function, and then there is the delivery function. So these are the experts working closely with our customers. That last function, the delivery function, has to be absolutely global. Yeah. So
Everywhere,
that
right?
is the first thing we're building and scaling in the US, right?
Hmm.
Then the research function is very much focused on the UK and UK centric, even though we have one member that is in the US already. We're global, great talent pool, and we know how to work cross continents, so cross time zones. Finally, on the product side, it's also important that software engineers, software developers interact with customers.
Hmm.
Sometimes a necessary part of the delivery, but often also that learning is very important to come back into our product. And lastly, in terms of business development, sales, go-to-market, and all of that, absolutely, that is in both continents.
Yeah. And you mentioned part of your early career was very focused on research, moonshot projects, very exciting things that may not be able to exist in the very near future. But when you moved over to automotive industry, it was very much, okay, delivery, this thing needs to work in the real world. For a startup, I imagine you have a blend of both because you mentioned research. How did you think about, from an AI engineering perspective, the someone who is very research focused versus someone who's very delivery focused on the AI side? Did you need to bring in both at the same time? Yeah, I'm curious your experience with that.
So we started on the delivery side, very much
Hmm.
working with customers, and and the research function was built maybe in something like year two. Gonna think back a little bit, but somewhere around there to really start building unique foundational technology for
Hmm.
PhysicsX. Because if you start, the company was self-funded originally, right? It didn't have investors and just, started it
Hmm.
like that. And so then, you have to generate income, right? And so that's why the delivery function was there first. And the technology was more around traditional simulation and traditional machine learning and things like that. So the research function then over time delivered unique abilities and unique tooling that formed the basis of what then got developed into a product. So the product function is now about a 2-year-old function, maybe 2.5 years old, something like that, that is building products, a software product. So that's how we staged ourselves through that. It's maybe a little bit atypical, typically maybe you start with research, or you might even start with product. A lot of applications of large language models don't need research. They just build applications around existing models, and it's very product focused.
Yeah,
Oftentimes
yeah.
it's SaaS, so it's you don't really delivery teams or service on.
Right. And I know we're coming up on time here, so I did want to give you a minute. If there's anything that we should look forward to, we just crossed over into 2025. So anything we should look out. How do I phrase this? If there's anything that we should look out for coming from PhysicsX, feel free. The floor is yours.
Thank you, Darius. I think there's things that we're all excited about, and we hope you will share some of that excitement. We're going to have an airplane version 2.0 that will release on this side of of the summer, and that will feature cool things around internal structure and such, adding motors in and whatnot. So I think that there's a lot of user engagement that I think will be enjoyable. The usual news that you will get about where we scale, what are some of our really interesting partners and work that we do. Keep watching. I think it's an exciting journey, and I think it's a phenomenal field. We're just very lucky. Sometimes the timing is just right, where you're happen to build just the right thing at the right time that becomes quite valuable.
Yeah, absolutely. And I love the use case. Love that we can explore. We talk about some generative AI use cases, which is the rave right now, but also look at other applications of artificial intelligence, particularly, in this case, within the manufacturing space. So appreciate you taking out some time to join us, share as much as you have. I think this has been super informative.
Hey, thanks, Darius. It's been a pleasure to be part of your podcast.
Absolutely.